Well, good afternoon, everyone, and welcome to the College of Business and Public Policy AI webinar series. And today the topic is digital twins. My name is Dr. Helena Wisniewski, and I am chair of the Management, Marketing, Logistics, and Business Analytics Department. I created the webinar series to create an awareness of the huge impact that AI is having across multiple industries and to inspire our students and faculty to pursue work in AI and collaborative efforts with our community. I have been involved with the development of many aspects of AI throughout my career and began when I was at DARPA, and I pioneered and directed advances in AI. And this continued when I was an executive at the Lockheed Corporation and a vice president at Titan and at Answer. Now I am sharing these experiences with our students. For example, I developed and teach the AI with Business Applications course, and I established the Alaska Data Science and AI Lab in collaboration with the College of Engineering. So it's a very exciting time at UAA and a very exciting time for everyone as AI is transforming our lives. At this point, I'd like to just recognize a few of our distinguished guests, Dr. John Offsinger, who's Dean of the College of Business and Public Policy, who will do our wrap-up. Dr. Mott, College of Engineering, he is the Dean. Associate Dean Terry Nelson, on department chairs in the College of Business and Public Policy, Dr. Carahan and Johnson. And from GE, I'd like to thank Mr. Santiago Tardin, the Director of Executive Platforms at GE Digital, for working with me to coordinate things. Thank you very much. And Mariah, who is our communications specialist for getting the word out about the webinar series. Before I introduce our speaker, just a couple of announcements. Please put your questions in the Q&A box. We will address all questions at the end of the presentation. And we also have a poll for participants. So if you could complete the poll, that will help us and guide us for our future webinars. So at this point, the moment everybody's been waiting for, it is my honor to introduce our speaker today, Dr. Colin Parris. He is a Senior Vice President and Chief Technology Officer at GE Digital and an officer of GE. As GE's Digital Chief Technology Officer, Dr. Parris leads teams that work to leverage technologies and capabilities across GE to accelerate business impact and create scale advantage for digital transformation. He also champions strategic innovations and identifies and evaluates new breakthrough technologies and capabilities to accelerate innovative solutions. Dr. Parris created and leads the Digital Twins Initiative across GE and is a board member of the Digital Twin Consortium. Dr. Parris was recently elected to the National Academy of Engineering as part of the 2022 class for his advancement of industrial operational technologies. Congratulations, Dr. Parris. He previously held the position of Vice President of Software and Analytics Research at GE Research in New York. And prior to joining GE, he was an executive for 16 years at IBM in roles that spanned research, software development, technology management, and P&L management. These included Vice President of Systems Research at the IBM Thomas Watson Research Division, Vice President of Software Development for IBM's largest system software development lab, which was 6,000 plus developers worldwide. Vice President and General Manager of IBM Power Systems, responsible for the company's 5 billion plus Unix system and software business. Dr. Parris holds a PhD in electrical engineering from the University of California, Berkeley, an MS from Stanford University as a Sloan Fellow, an MS in electrical engineering and computer science from the University of California, Berkeley, and a BS electrical engineering from Howard University. So you have really impressive credentials, and we're really very excited for you to present digital twins and all you've done in that area. So I will now turn the webinar over to you.
Thank you very much, Elena. Well, it is my true pleasure and honor to be here, and on your series. So I'm hoping I can provide some insight to the honored colleagues here as well as your students. And so with that, let me sort of bring this up. You will let me know if you can actually see the screen share. Okay, how does that look?
Perfect.
Excellent. Okay. So thank you. I think Helena gave me a way too gracious introduction, but there are essentially two things I do. One is that I look at new technologies and especially around AI, and I try to figure out how to put them inside a business process that can deliver value. So my focus on technology is one in which I actually am delivering business value for the GE company. And the second thing I do is I also aid in digital transformation. Even if I give you the technology, without a change in the business processes themselves, there's very little that you can do to deliver really sustainable value. So I'll talk today about both of them. And rather than talk across many industries, GE is in many industries at this point in time, I'm going to focus on one. I'm going to focus on the energy transition, because I think this affects every one of us across the planet. So that's what I'm going to spend my time doing here. So let me tell you a bit about what I will actually do. So here's the flow of the conversation. I'll talk about the market forces. This is really the motivation of why is it, that these energy transitions are going to be really impactful for us and for generations beyond us. Then I'll give a definition of what digital twin is to us. Again, there are many versions of digital twin right now when you look at what's happening in the industry. I'll talk about it, and I'll talk about the business value, the relevance of it to the energy industries. Then we'll talk about digital transformation itself. How do I take this technology and take the notion of business processes and really extract value? It'll be a combination of two cycles: the cycle of the digital twin, building it and deploying it, and the business cycle, actually getting the adoption and delivering value. Then I'll end by a bit about how do you accelerate business value, right? How do I actually increase business adoption and lower risk? And then some of the emerging technologies on how they interface. So that's the span of things. So I'm hoping when you leave here, you really understand how we're trying to insert AI into this specific business value stream. So let's talk a bit then about the market forces. Here's what motivates, the discussion and me, because I am very, very in tune with this energy transition. I think it's something that's profound. There are several forces that are occurring on the planet right now, and I think the top row, you'll see all of them, right? This notion of decarbonization, whether you look at it from a point of view of climate change, or you look at it from a point of view as there are a profound number of weather events that are happening, and you have to figure out a way to manage it and protect from that in the future, you have to think about it. And because of decarbonization, what we've done is we've introduced a number of renewable sources of energy, right? By that, solar sources, wind sources, even hydro sources. Whenever you introduce these sources, there are other effects as well that happen. So this growth in renewable growth across the planet is a big factor that's driving this energy transition. We're trying to move away from fossil fuels. Other aspect of it is digitization, right? The notion that we are connecting these devices across a variety of places, whether they be smart sensors, whether they be actual devices like electric vehicles, we're connecting that, and that gives us a better understanding of the state of our energy needs, right? Because I have these devices, I can tell how much electricity I'm using now, and I could even potentially predict how much I will use. And so with the increase in the digital capability that I have, how do I actually use that to my advantage in the energy transition? Third aspect is decentralization. So right now we are creating these massive wind farms, these massive batteries that sit on the grid and connect to the transmission grid. But also, in every one of the cases you look at, in the residential areas, you have people putting solar panels on their roofs. You have them buying electric vehicles. You have them buying heat pumps. There's a variety of things that are being attached to the grid in the residential districts. In the commercial district, even if I look at somebody, for instance, like an and Amazon has a data center. They are actually buying renewable energy to power the data center, and it's being attached to the distribution grid. So now I have a variety of sources that can both consume as well as generate electricity, that's being provided in a more decentralized place. Rather than having 15 or 20 large power plants, now I have a variety of smaller entities attached to the distribution grid that are also providing power. How do I think about that decentralization? And then the last thing is electrification. The notion is, rather than run my car with fuel, I'm going to use electricity. Rather than run my house with oil, I'm going to be using some form of electricity with heat pumps or other type of technologies we have. So these are the forces that are driving this energy transition. And in some ways, this is inevitable. In GE, we have a front seat for this. We right now have 7,000 gas turbines, the largest fleet on the planet right now. And these are turbines generating using fossil fuels, but also we're working on other fuels, such that including hydrogen, so that we can generate with the least amount of carbon. We have, I think, right now, maybe the largest active renewables fleet, 52,000 wind turbines across the world. We also have a significant amount of the grid software. There's software that controls the transmission grid, controls the distribution grid, that helps build the markets, allows the trading of electricity. All of those pieces of software that GE has been building for the last 30 years, and about 30% of the world's power, 30% of the electrons, are controlled by that software itself. So we have a front seat to it. So this transition is driving us forward. And as a result of the complexity that you see, we're adding, bulk renewable sources, we're adding distributed renewable sources, we're adding a variety of new plants, a variety of new equipment. People are using it in their homes. The complexity of it is astounding. So we have to use some of that digital capabilities. Hence, to manage this and to optimize it, we began with the creation of something called a digital twin. So let me talk a little bit about what this is. Right now, again, before we did find ways to create the electricity, manage the electricity, deliver the electricity. So you're asking what's changing? Why is it that we need AI inside these scenarios? Well, let me give you a couple of views. One is there's a significant amount of new dynamics. That's the answer to what's changing. There are dynamics, for instance, in the sources of electricity and the demands of customers. They want more green energy. So you're looking at the fact that we have to have more renewables. Then there is environmental demands. There are significant weather events that are occurring, and allowing us and forcing us to try to manage around those weather events. The number of storms have increased tremendously. And with the storms have increased the business, impact as well. In 2020, the number in the US right now, damage as a result of storms to utilities is $95 billion. That was the number for 2020. That's both damage directly to utility and then liabilities. Again, in many cases, these utilities pay liabilities when they can't deliver this energy after a certain period of time to the businesses that they deal with. So you have conditions around the type of energy, conditions around the environment changing. You have changes as well in the government regulations. Everyone is saying, I have a net zero target and I want to deliver that. There are changes in what your employees now want to know that you're delivering value and doing the right thing for the planet. And again, you have also changes in terms of investors. Investors are saying, well, with ESG, I want to know how you're doing things right. All of these are forcing a complex situation where there's lots of dynamics, as well as at the same time, I have hardware that's 20 to 30 years old. Generation plants are, it can be anywhere from 20 to 30 years old for a combined cycle gas plant. It might be a wind turbine, might be newer, as in 15 years old, a wind farm. There's newer technology on the grid, but some of it is there for quite a while. The software is between 5 and 15 years old. In the grid, you have some instances where the substations are 40 years old. And I'm constrained. I'm constrained by contracts I have, government regulations I have, and a workforce that's had the same work processes in place for the last 10 years. So with the massive dynamics and these constraints, what do I use to actually, figure out a way to get around that. And that's really going to be digital. Can I use the AI and the insights I get from it to react fast enough to deal with changes in the weather, to deal with changes in cyber, to deal with changes in what customers want, as well as in changes in what the government wants? And so this is the way we began thinking about these things known as digital twins. So what's a digital twin? So what a digital twin is, it's a virtual representation of a real world asset, a physical entity, right? And so when I think about it, it's that way to represent, and not only represent, but it's also the ability to understand and gain insights from it. That's one difference in the definition you have when it's applied by us in GE. So if you look at the picture there, what you see is that we're using knowledge or insight we've gained essentially from designing, manufacturing, installing these assets and running them in some cases, as well as the data that's coming out of them. And that combination of the physics and domain knowledge with the data and machine learning capabilities from the data derived from the operation gives us insights. It can give us insights as to the remaining life on a part. Insights on, is the part performing at the right level, or is it being utilized in the right way? And if I can gain these insights from a digital twin, right, what I can do is then do an action. It does you no good if you have an insight, but you don't take an action. And the action could either be I do a repair function, I can actually tell an operator to make a decision, or I can go directly to the control system of the asset and make a decision. And once I do that, I get feedback, and that feedback is captured in data. And so that's a learning loop where I can have my digital twin, which is really a living learning model of an asset, become better. And then essentially I can also take some of that feedback and give it to my design teams and design it better. So this is what a digital twin is: a living learning model of an asset you have out there, or a network you have out there, or a process you have. And we're using AI to drive that even more, because AI allows us to learn at a much faster rate and get insights we would normally see. So let me tell you how it's being used. So it's one thing to say I have a learning living model. That's interesting as a technologist. How do I actually use that to create business value? Here's some ways. So we talked about in the energy transition, we're enabling much more renewables, right? So when I have these wind farms, what do I want that digital twin to tell me? Well, the things I'm looking at, and especially with wind, because wind is where you have a sort of free fuel. So normally if you have a gas turbine, you're going to have to put in some form of fuel, and that fuel is characterized a certain way. Wind is not. What's interesting about wind is if you go to a location, you'll realize that the wind at different heights, if I measure the wind on one of these wind turbines, at the 10-meter level going all the way up to the 30 or 40-meter level, the wind speed varies based upon the height you have. The wind speed varies based upon the literal time of day. The wind speed varies based upon the season. The wind speed varies based upon where you put this actual wind turbine in a digital farm. So the wind itself is really a very dynamic thing. So what you're trying to do is you're trying to create a digital twin that actually gives you a view of, with all these changes, what is the correct parameters, what's the correct control settings I should have on the turbine to get the most power. And that's called AEP, the annual energy production. Also, you want to figure out with the same digital twin, when should I maintain it? If I wait too long and a crack develops on a blade, that blade may liberate, it may break, or it may slow down production. Could I detect, using the sensors, when something seems to be wrong with vibration, so I may have a potential crack? Can I fix it early and reduce the turbine cost? Also, if I fix it early, rather than waiting and fix it later, can I reduce the repair cost? So these twins can do things that directly impact your business value. If I look at optimizing asset productivity, the middle column there, this is really thinking about the digital twins in the context of a gas turbine. Can I actually understand the parts in that turbine? And the parts really, because I'm doing combustion, because I'm actually putting in a fuel, igniting that fuel, that explosion takes place, which causes the turbine to rotate. there is a lot of damage that occurs. So can I actually understand with a twin, early warning on damage that could potentially shut this turbine down and basically do predictive maintenance, predict when it might fail, predict what might fail and take an action before that fails, or simply have a part ready for when that fails. It's amazing, but if you look at the lead time for parts inside some of these turbines could be as much as 16 months. So if you actually have something that occurs and you don't have a part, that system may be down for quite a while. Can I actually then use the twin as well to reduce emission, especially noxious gases coming out, because I have a certain type of government, compliance to which I must address. And then again, can I use a digital twin to increase the power? Based upon the fuel temperature, as well as the fuel splits, how fast I put out fuel, I actually can control how much energy, is emitted by this turbine. So these are all things the digital twin can do to deliver value. Last part of this action is actually transforming the grid itself. So even if I generate the electricity, I've got to find a way to transmit it over long distances, which is the transmission grid, and then step it down at a transformer and transmit it through the distribution network so that it can be consumed by residential users, commercial users, industrial users. So in looking at that grid, can I actually have a digital twin that gives me a view on the stability of the grid? Now, the grid must remain at a certain frequency, whether you be in the US at 60 hertz or Europe at 50 hertz. And to maintain that frequency, the digital twin itself can actually begin to look at how many of these things. Now, frequency, can be maintained easily with synchronous machines, these large machines that spin, right, in terms of the gas turbines, because when you're using fuel, you can get them to spin at a rate where they always spin at the same rate. Now, with a wind farm, because the wind speed varies, or sometimes it doesn't actually blow, that wind turbine will deliver energy not in a synchronous manner, but in an asynchronous manner. The same thing with a solar farm. When there's cloud cover, less energy is generated. So how do I actually stabilize the energy flow? Because all of our appliances operate at the same frequency. So I can use digital twins to get me the right stability as well as security. How do I do it in a way such that I don't have any, things that occur on the grid with fake information coming in? Because I understand, what's the level of capability of each of my assets. The other thing is, how do I keep the power quality? I just mentioned that we actually can have variations in frequency, but we could also have variations in voltage. So I can use a digital twin as well to tell me how to balance which assets I have turned on, what power do I buy a day ahead, 5 minutes ahead, and then how do I dispatch that power so I have voltage stability? And finally, how do I do it in such a way that I can have the lowest economic cost? Right? So again, the twins are doing all of these things to deliver business value. Now, the other aspect of that is, well, okay, Colin, that makes sense, but where does AI play into this? And so while this isn't a technical talk, it's always good to understand the role AI plays, right? So you think of AI, you think of, basically the reason it's called artificial intelligence, it's a reflection of the intelligence that we believe is innate in humans, right? So there's a level of visual intelligence around computer vision. There's a level, of understanding in terms of I can read things and learn. Well, this is natural language processing, either, in the written word or the spoken word. There's a view of we think differently, which is machine learning, and there's a view that we do things, which is robotics. So all of those and different dimensions around artificial intelligence added to some, powerful statistics give us the ability to do things that make sense. So for instance, we use these AI technologies in imaging, right, with computer vision to actually do the right industrial inspection. We can have the computer vision system look at a part, and rather than have a human tell us, for instance, it's damaged, we can actually have the computer say, this is the type of damage, and this is the length and the breadth of the damage. Really hard for humans to do that and do that well. I can fly drones to the top of these large wind farms, and I can have them look at the blade and do aerial inspections, right? Also with natural language processing, a lot of the work we do is written. So we have manuals, and then when we do a service report, we write things in the service document. We have to provide invoices to people when they actually perform repairs. Can I have, natural language processing where I pull up that text and learn from it and create contextual reasoning? I can see the relationship between here is a certain model of turbine, here is the damage that was done, here's the repair and how much it cost. And so there's a linkage that allows me to see turbine, parts, symptoms, cost, right? And so this is how we use natural language. Time series. We use a lot of the AI capabilities to actually help us, because we create a lot of time series, which is I take sensor data every millisecond or every multiple milliseconds, right? And in that sensor data that comes across so many minutes on that time dimension, that's a time series. Can I use machine learning to understand what's in it, patterns that are in it, to do forecasting, to do prediction, even to do root cause analysis with diagnostics and prognostics? Same for robotics. Can I now use that capability and have the robot inspect or repair? Then there's the notion of the science around the AI. So in many cases, I need the AI to be robust, right? I can't have a model and the model is delivering value and the value that gets delivered, is not accurate. How do I ensure that it's a robust model, that my data wasn't biased, that I had enough data? How do I explain it? Because again, some of this equipment, you're talking about hundreds of millions of dollars. So when I go tell a chief engineer, look, you need to actually shut down your plant because there's going to be a failure in 2 days from now, and so there's a significant amount of, revenue at risk. How do I explain what the AI said? It just can't be a black box to her or him. How do I have it physics informed? In many cases, when you look at big data can detect patterns, but the patterns are spurious. They're not relevant. So what you need is an understanding of the design of the system, the manufacturing, and how it is actually being operated to actually say which of these patterns is relevant. So this is physics informed AI. And then the notion of decision automation, whether you actually say it's decision, assistance, augmentation, or automation. A lot of these are the things that we want as the output. How do I do optimization? How do I know when to reconfigure the systems I have? How do I know when to do maintenance? How do I know when to do workflows around repair? So all of these things in AI is what we use to get that value I talked about. So let's actually, understand what that value is, because it's always good when you put a few dollars to things. So let me tell you what we actually do with the digital twins we build. So remember, it's a combination of physics models we know from design and the AI capabilities. The AI capabilities give us insights into patterns. The physics begins to tell us what patterns are relevant and so are believable, that allow us to get more than a correlation, but causality. So it's the combination of those two that make a difference, right? And now once you have the combination of those two, what action do I take that actually yields money? So we think about twins delivering value in 3 ways. First way is an early warning. Can you give me warning of a problem before it occurs? This way I can prepare. Because again, in the industrial worlds we live in, you need time to take an action on something, right? You have to have the availability of parts and skills. Early warning is very powerful. Next thing is prediction. Can I predict a failure of a component or failure of a system? This way I know how to plan and manage that and minimize costs. Can I actually predict the lack of performance or potentially better performance in a system, especially a wind turbine? Very good thing to have. Or can you give me a way to dynamically optimize? How do I actually balance these loads so I get the most renewable assets, because I want less carbon, at the lowest price with the stability where my frequency on the grid stays the same? These are some examples. Let's look at the first one, hydro. So looking at a hydro plant, what I'm doing there is understanding the physics of the hydrogen plant as the water treatment plant or the water processing plant. And what I want to do there is take that capability and actually take a bit of data with it. So you see some things like generator load, the bearing temperature, the vibration, using some AI capabilities, give me an anomaly store. So give me the ability to tell when something is going wrong. Now, usually you can tell when something is going wrong when a big sensor tells you a problem. How about if I can detect when there's something slight that's happening? So I'm using the twin to create small virtual sensors, knowing the physics, where I can't put a sensor on this hydro equipment. This is like a dam, it's huge. I can create a virtual sensor. That virtual sensor gives me an early view. I actually use feedback to check that view. And then I say, okay, based upon that, I'm going to take an action. And so we can detect this admission valve failure. And every time we detect those valve failures early, we can quickly say, because when you have these valves failing, there is a lot of air bubbles that get into the system, and those air bubbles begin to shake the machinery and damaging the machinery. So if I can detect them, each event saves me roughly $100,000. And I have a lot of events. And so if I don't get to the events, I shake those bearings shake the system. I've got to go in and fix one of these massive turbines that's on a dam, cost a lot of money. Early warning. Next one is life prediction. The notion here is, can I actually look at my combined cycle plant and find a way to determine what's the state of the part? Because what's happening now with the fact that you have a lot of renewables on, before we used to build these plants and it was so efficient, you ran it all the time. But now for the sake of decarbonization, I'm only running it when I need to. So I would prefer all of my energy be generated by the renewables, by the wind and the solar, as it produces no carbon. So because now I have now begun turning these plants on and off, I don't have a profile of the damage. So can I use a twin to predict that? So can it give me the state of the part life and then what I can do in order to actually use it more efficiently? And if I do it the right way, what I find is that I can actually find a way to make close to from 1 million to 3 million based upon the size of the plant profit a year. Real money when you consider, several of these utilities may have 15, 20 plants spread around the place. That's a nice chunk of dollars. Performance prediction. Again, the wind is changing across the wind farm. So you have 20, 30 turbines in a small wind farm, as many as 300 in a large wind farm, and this wind is changing. How do I optimally understand with the changes in the wind, how to set the pitch to your set point such that I get the maximum performance? And if I do that right, I get an increase in 1% improvement. You may think that as small. 1% on these large farms adds up easily to millions of dollars per year. And finally, dynamic optimization. If I can optimize the grid, it means that the grid really is buying a lot less energy. And if buys a lot less energy because it can stabilize, what then happens is that it can translate that into lower costs that you can get, right? So again, in some of the grids we look at, this is millions saved per year. So all of these legitimate ways in which you can use the AI and the digital twin capability to get you into a profit stream in which you're seeing value being delivered, right? And in addition to that, you're reacting faster in many cases. So let's talk about that. So we've talked about the fact that I can use a digital twin to actually capture value. Okay, so there's a cycle in which this happens. Usually what tends to happen is that you do it as a pilot first, right? Because you have the idea. You want to take the idea and you want to actually validate it, right? Which means, does it really work? Then from validation, you want to say, can I verify it? Well, is it compliant in such a way that, I'm not, I run the digital twin, it works, it saves me money, but it's producing more emissions. Okay, so we do the verification on it. And then from the pilot, the notion is, can I legitimately deploy this and then scale it? Scaling is important because sometimes when you do a pilot, because you're doing a pilot on marginal, assets, I already have, I should say a large cloud capability. I really have some engineers. I can pull a few of them off and I can have them do these things. It'll cost me a lot less. That's one thing. If I have to go to scale, if I have to do it now on 400 turbines and collect all that data and do all that computation, that's a whole different cost profile. So can I think about how to do it at scale and get that right? And I've got to collect data from many sources. How do I collect data at scale? Non-trivial. And then I've got to learn how to manage it. how I've got to think through what could go wrong. And when it goes wrong, what do I do? What happens when I am running this twin and all of a sudden there's a data drift? Somehow the data that's coming in, maybe my twin depends a lot about around environmental data. And for whatever reason, wind speeds have increased. Is my twin still valid? Or what if there's model shift? So there's a data drift. There could be a model drift as well, in that all of a sudden I change my business model. So it's not that important that I actually reduced a lot of maintenance costs. Maybe the repair cost is the biggest thing, because what's failing are my warranties. How do I then tap that or change that digital twin? So that is the digital twin cycle. How do I make the technology work for me at the best performance, but understanding the cost and the changes? Now I have the other problem. We're going from the left-hand side to the right-hand side. How do I actually get into the business process where you have humans doing the work and actually influence that business process? One of my first experiences using twins at a really industrial level, we're trying to figure out, we have these large, gas turbines. And again, what you have to do is these blades break, you have to replace them, you have to do maintenance, you have to repair them. And you look at the process by some of the customers, and the process was, well, there are 4 people who sit in a room and they say, historically, we think this is going to happen, or I have a gut feel that, the inventory that you'd need, I'd need about 400 extra parts. Turns out that year you needed something like 800 extra parts. Why? Because, again, some of these things you don't count on show up, right? So for whatever reason, somebody built some site that was putting contaminants in the air a couple of miles away. They were landing on the blades, things were going wrong. The summers were hotter over the last 3-4 years, so the damage, due to combustion was greater. So you can't do it the normal way. You've got to change your business process. I introduced that insight. Now I've got to say, well, based upon that insight, what do I do? Do I now look at the insight and do I say we're going to try it, or we're going to actually have the human engaged at the right time? I need to collect data to do it at scale. Do I have the right data process? Should I actually change the data process? Before it was people writing things down on a clipboard, writing them down, on spreadsheets. Now I have to change that. So the entire business process has to change. And once the insight comes in, the actions you take are the changes in the business process. You look at the outcome, you get the feedback, and this is how the process scales. And if you scale it well, if you scale it on the digital twin cycle, in which your twin is getting information and learning and giving you insights faster, and then you scale it on the business value cycle where you can deploy those and get more benefits, you've essentially created a business moat in which you have competitive differentiation. And the differentiation increases because the more data you get is the faster you learn. If you learn fast, it means you can respond better. If your process allows that faster response, you continually get better. So you have a moat in the data, you have a moat around your process, and with the outcome, you can change business models. You can go get deals you never got before. So this is the notion of building a framework that combines those two. So keep that framework in mind. To build that framework, this is the business value cycle, is hard, because this is the part where you've got to deal with humans, right? This is the part where, and again, humans, have powerful in the business cycles because of the intuition and the fact that humans can learn very quickly on 1 or 2 examples, but also humans create processes. And when you think you may have one process, you may in fact have 4 or 5 different processes. And when you think you have the data in one spot, it may not be so. So what we've done at GE is we've created a business transformation process that combines lean and digital. So with lean, the essence of it is all about removing waste. But to remove waste, what you do is you do a value stream map. You look at every action you take, from the inception, the start of the process, to the end where you deliver value, and you lay that action out and you understand all the characteristics. What data was used? What is the timing of that action? Who actually does what? What are the key determinants? So this is what you do in lean. And so with that, I'm able to understand the process. And then with digital, I'm able to introduce digital into that process at the right points to remove waste and to add value. So the combination of lean plus digital actually gives me digital transformation, because digital transformation only occurs when I have taken the digital aspects of things, the data, to get insights. And then when I translate that insights into a process, a business process change that allows me to use that effectively. So this is lean plus digital, and that drives improved margins. What we did at GE is we created a process around that. So on the left-hand side, what you do in the process is you start by saying, what are the top value problems? Where are you losing the most? Oh, why is my margin so low? Or how do I take out more cost? Those are the largest part of the process. You define where you want to focus. Second is a value stream. Who does what when? What's the timing? What's the resources being used? Lay out the entire view of the process. Then after that, we go into structured problem solving. Using Pareto techniques, using FMEAs, what's the biggest source of waste you have? Or what's the biggest opportunity you have? Let's tackle that first. And so then we get to the business strategy part. Okay, if I'm going to tackle that, let's talk about the process. Let's talk about the key performance indicator. How do I actually get the right metric so I know if I'm doing well? It makes no sense if you don't have a benchmark and a destination point to talk about the fact that I'm doing better. I need to know where I am. I need to know how I'm going to get there. And those are key performance indicators. And then I do a number of things called PSPs, a problem-solving process that allows me to continually improve that value stream. And so we do that the right way when you combine digital. Underneath every value stream, there's a sequence of systems that collect data. It's amazing when you actually, ask people where they get their data from. And they'll all tell you, well, I mean, there are 3 or 4 fundamental sources. We've done work with customers in which it went from 4 systems of records to really something like 23, because every region in the world had a different one. Here, 80% of the data is right, but the other 20% had to be collected or massaged by humans. There's a bunch of hidden factories. So we collect everything in that digital connection all across everyone involved, and then we do the execution. We start with the problem solving. We actually do a macro VSM. So micro VSM, I want to go down into sub-processes and see what everybody's doing, what data they're using, what decisions are they making. I'm going to give you a data flow so I know when the data is used. How do I use that data? Then I create an action plan. And usually in the action plan, what I'm trying to do is in many ways have the humans put in as little data as possible, because that's when problems occur. Have the data not be transcribed between systems, integrate the systems, right? And then I'm trying to capture human knowledge, tribal knowledge that's not captured a lot. I'm trying to get that and codify that in the algorithms I have. And then I constantly learn. And that's when I actually get the value. And then I scale it by having a sustainment process. I manage that process daily. I do operating reviews. And the power of digital is that the digital is in the process, but at the end of the day, I come with a dashboard. So you're constantly seeing what's going on. I actually have a way now, because I've captured the data, to constantly put AI against that data to get new insights for new opportunities, and then finally to continuously learn. Let me give you an example here. One example we had with blades, part of the challenge we have is that you have got to do accurate inspections. You fly a drone up to the top of these large wind turbines, and what you're doing here is you're taking pictures of the blades. And we have an AI system that takes the pictures, and the AI system automatically detects a defect in the blade. And then from the inspection, what you want to do is generate an inspection report and take an action, disposition. So once the detection of the problem, the AI system then says, we think this problem is a severity 5, and it writes that in a report, right? In many cases, we simply take that and just dispatch it into the SAP systems and send out people to work. If the AI system isn't too sure, it then hits a button and basically pulls a human into the loop. Human says, I don't think so. Yes, I think so. Go ahead and do the disposition, do this repair. And then we actually go on and we quickly monitor what's going on to make sure it's safe for a human to go up there to fix that blade. Then we repair and replace it using a digital twin to figure out the right scheduling of resources with the right set of materials. So this is an entire process we redid, instituted, integrated the data inside of it and the insights inside of it. And now with that, we're saving another $30 million a year, just doing this right. So I've just given you a profile on how you take a look at a digital twin, how you actually get one, and then how do you actually tie it into the process. Let me talk a little bit about accelerating value for you. So one of the issues every time you use AI is people actually get worried. They say, well, first of all, first argument is AI is going to take my job. Well, no, it's not. Right? Again, it'll do some mundane things, but again, there's always the part in which new things show up. There's always the piece in which the problem has been too complex. So it's still a good way is in removing jobs. But the second thing is, how do I know that this AI system can cover every case? Well, we devised something known as Humble AI. What Humble AI is, Humble AI, you usually build a model around a zone of competency. I have a lot of data between these wind speeds, as you can see on the diagram. So think about this. So I usually on average, a wind speed is between 5 and 6 meters per second. So I collect a lot of data. So the models I build are going to be very good. What if the wind speed goes up to 8 or 9 meters per second? That's outside the region of my competency. So the AI system knows, I'm outside my region of competency. So what I'll do is I'll turn over control to a deterministic algorithm or a human, and then I will ask that human to collect more data. And so I can learn to expand my zone of competency because now I can tune the algorithm. This is Humble AI. The AI knows its zone of competency. Inside that zone, it executes. Outside the zone, it sends control to the human or another, most likely physics type algorithm, and then it collects data, learns, and gets better. This way, you're encouraged to adopt because within the zone, people feel comfortable. It's a small zone. All right, let the AI run outside the zone. All right, the AI needs my help, and the AI gets better bit by bit. And that is business adoption. The other way we worry about is business risk. And here's an interesting capability we've developed at GE. It's called Digital Ghost. So what this is that I have the digital twin of a gas turbine. But what if I am hacked? What if at some point in time somebody hacks one of the sensors? Well, the digital twin knows, because it knows the physics of how these things operate, and it knows, well, something seems to be wrong because by the law of physics, I have 3 sensors saying one thing, the fourth should say something different. So at that point, I actually take the control unit, and I have the control unit, rather than listening to the sensors from the turbine, listen to everything from the digital twin. So the digital twin itself then takes control, and it says, sensor number 4 is not good. So I'm going to drop that sensor, and I am actually going to use the 3 sensors and then tell the control signals based upon these 3 sensors. I'm going to go in a conservative mode. You tell me the control actions I need to take to still produce power while I run this turbine. So what you see happening here is that we're using the laws of physics, which is we know how we design the machines. And so if you have to actually fake a sensor, then somehow you've got to change the laws of physics for us not to know. And I'm using those laws with the digital twin to say we know a sensor has been hacked, or it may be bad, but more than likely it's hacked with this pattern. We tell the control system, ignore that sensor, listen to what the digital twin is telling you. We run the asset in the right mode, so the asset is running safely. It may be less, powerful, and we deliver value that way. We have done this. We've gotten money, significant money from the government with this. We have done it on our massive test stand with one of the large machines we have. We actually attacked 3 critical sensors, more than 1, right? We actually discovered the attacks. We were able to neutralize the sensors, and this was some work that we did in combination with the Department of Energy. Again, finding ways to actually manage, the proliferation of AI in a way that it doesn't disadvantage us. Now, let me hit one more topic for you. This is the emerging technologies. So I've talked at length about how we can use AI to get us better. So what are the things I'm looking at in the future? And this is 2, 3, 4 years out. And I have 4 sort of edge conditions. What other new technologies are top for us? So one of them is upper left, synthetic data. we can't generate enough data about, extreme situations. We don't have that data. So is there a way I can synthetically create that data? Now I can use my test stands, because I can actually nearly half destroy a machine there to create the data that I need. I can also use the national labs. We work with them quite a bit because they have high performance computers that can do massive simulations that almost get close to, these extreme scenarios. Or I can actually use things like a generative adversarial network, two neural nets that one actually, is creating data and one is trying to determine if the data is fake or not. And by using both of them together, both get better. So there's a number of ways to create the synthetic data. And the more synthetic data you have, is the better you can test your algorithms, so that when once in a lifetime storms or cyber situations show up, the algorithms respond even better. Synthetic data is a big area and it's being used everywhere. If I go across to the right-hand side, well, let's go down first. After synthetic data, edge AI. I need to find a way to run a lot of things at the edge right now, because that's where I'm collecting data and I don't want to send it all the way back. I have latency problems. But also I want these special purpose-built independent edges. And these edges are built such that it's low power. It can stay in hostile environments, but it does all the compute and the networking. And so I could get insights right there to give it to teams and assets right to the edge. These things, can use things like TinyML is a new form of ML that works on microcontrollers right now with low power consumptions. And then you add to that model compression, where you take these large, neural networks and you compress them so that they run accurately for the situation, but on a smaller system. So edge AI systems are huge. And if I go all the way to the bottom on the other side, I'm thinking about this next-gen wireless. So 5G gives me more data volume and better latency in many cases, but also these low Earth orbit satellites are coming up. They're giving me access in areas where I would not have access. Some of these wind farms in very remote places, right? How do I get access to them all the time? How do I see also what's happening? Because I can get visualization as well as data. So can I use that combination to get much more data, greater latency, so I could react faster? And then finally, if I get to the top, how do I bring the human in that AI loop? Because we talked about the fact that you can have as much digital technology, but unless you really add to that the change in the process, the human process, how do I combine that? So I talk about decision support, or decision assistance, or decision augmentation, or decision automation. I go from the AI helping, the person to actually see what's going on, to helping the person figure out solutions to the problem, to actually doing the problem by themselves after we've had enough understanding of the problem. So how do you do that and balance risk and opportunity at the same time? So with that, I'd like to end here. I know I've given you a lot to think about, but what I've attempted to show is that these digital twins can find a way to monetize data and AI capabilities, especially in the services and operations business processes. If you look at it historically, AI was used by Amazon in the commerce process. AI was used by Google in the advertising process. AI is used by Apple and Netflix in the entertainment process. We're using AI in the service and operations process, right? We have to integrate the human insight with the AI as part of continuous learning. And the other thing is that the need and trust are key to adoption. Needs are growing. We have less people with the great resignation, inflation. So you've got to do more with less, cyber challenges. But trust is emerging, as I said, with some of the new technologies. And with that, I know I've gone a little bit too much here, but I will stop at this point and I will turn it back to Helena. Hopefully that was enlightening in some way. Helena, back to you.
All right. Well, wow. There's one word I have for your presentation. It covered everything that I could have requested or wanted to see, including how AI is integrated into the digital twins, how it really affects the business process, how it brings profit to the company and efficiency. That was absolutely terrific. I really, really enjoyed it. Thank you so much.
My honor.
So let's go to the Q&A, and then after the Q&A, we'll have our Dean of the College of Business do our wrap-up.
Okay, so our first question is, are digital twins vulnerable to cyber attack, potentially seeding incorrect information about infrastructure or procedures that businesses might act on?
Very definitely. This is why we started that work on the digital ghost, right? Because what we believe we were doing there is that you can fake the data coming in. You could also fake control signals. The capability of digital ghost is that because we design the asset, we know how it should work in physics, right? So for instance, if you have 3 sensors, and this sensor on the outermost side is saying 200 degrees, and the one on the other outermost side is saying 300, the one in the middle can't say 600. That just defies physics. So because we have those insights, we can begin to quickly tell what's going on in a system. And then occasionally we perturb the system. We deliberately change things like the fuel mix and everything else. And we know what we should inspect, what we should expect to be the response. And if it's not, then we could begin to tell, who's tampering with what. So I very much, agree. This is a big challenge we have, and so we've been doing things with ghosts and other things with the government on that.
What is the opportunity for early stage entrepreneurs in rural areas in Alaska to find a niche in digital twins?
Oh, I think there may be, well, I wouldn't speak directly to you, but in terms of what is in Alaska, but I'm thinking of a few things. So for instance, you're going to have an energy transition challenge, right? Without doubt. And so as you think about that, and I think people are going to, want to do things like have distributed energy resources. People may be putting in more efficient heating systems, cooling systems, more efficient sources of energy, less carbon. How are you going to manage those things? So there will be opportunities just with the residential folks. How do you get digital twins that actually help them reduce the amount of carbon, or even just reduce the amount of energy that they want to spend their money on? So digital twins are there. I will take it and say, what about your sewage systems? What about your water systems? In every case that you have a system that's running and providing value, there's the opportunity to put a digital twin in place that actually reduces, the costs. Even logistics systems right now, with supply chain being a problem right now, one of the biggest discussions is, how do I manage my fleet, of cars or my fleet of trucks that's moving things around in such a way that I can deliver the most things with the least cost, right? Especially as fuel prices rise. So I think a lot of it is in actually looking at the processes that everyone has around you, whether it's processes related to the industry you have, and understanding where's the waste and building a digital twin that replaces the waste. That's what I think at a high level.
So we have one last question. Can you envision a sort of meta twin lifting the technology of much larger systems in the future?
Yeah, a lot of discussion has been happening around that. So for instance, the grid is one, a meta twin. We know there are people who are using these low Earth orbiting satellites to actually understand, how wheat is growing. So you're trying to look at a variety of things. So can you model parts of the agriculture on the planet with a digital twin and understand then, what fertilizers you bring into place? There are people who are using the digital twin now for humans, trying to, in fact, I think a couple have been using it in the spread of the pandemic itself, because the pandemic, the COVID has been viewed itself as an entity, and that's the way the virus spreads. Can you use a twin to model how that happens and know what to do with it? So there are many examples that are happening right now with these meta twins.
Does that complete all the questions, Claire, for now?
Yes, it does.
Okay. Well, Dean Nalsinger, you're up.
Thank you very much. So this was a great presentation for me. Number one, I got to start to relive my my first professional days, which I was electrical engineer in a power generation and distribution company. So that was great for me. But obviously learning all about these digital twins and their uses, and then connecting it all into business value and value chains and things like that was tremendous. So thank you very much, Dr. Parris. What a wonderful presentation. And then I also want to thank Dr. Helena Wisniewski for another great AI webinar, which just adds to the great ones we had last year. And I'm expecting some more wonderful things coming up for the rest of this academic year. So thank you very much, Helena, for putting this together. And then, of course, I want to thank all of the people sort of in the background who make these webinars and media and all of that stuff work. And when they do their jobs really well, you don't even see them. So that's thank you to all you people too. I guess that winds us up, huh?
I think it does.
Thank you again. It's my pleasure and honor. Have a good day. Take care.
You too. And thank you to all our participants. I hope that you gained a lot of insights from this webinar, and we'll attend our future ones. So everybody, have a good rest of the day.